Welcome to the final stage of the 33-day mathematical engineering sprint. You are done learning isolated axioms. Today, the focus shifts to systems integration. In applied engineering, physical challenges do not arrive neatly categorized by textbook chapters. Systems integration is the mathematical theory of coupling distinct analytical engines together to solve those complex problems. The core mechanism relies on continuity. The mathematical output of one distinct structure becomes the input for the next. This pipeline unifies your coursework. The spatial rules of Part 1, Algebra and Matrices, feed directly into the dynamic analysis of Part 2, Calculus and Probability. Your structural goal is to take these separate mathematical domains and forge them into a singular computational framework. The practical mandate for today is to compile this framework into a standalone, object-oriented engineering handbook. Coupling these engines turns mathematical concepts into a set of tools capable of driving real-world systems. To understand this pipeline, we must define each engine's role. Linear algebra provides the spatial framework, as matrices handle state tracking. Calculus is the kinematic engine, dictating how structures change. Probability forms the error correction layer, managing uncertainty to keep outputs accurate. The absence of any single engine causes system failure. Without space, there is no structure to measure. Without kinematics, there is no movement to track. Without probability, the data is entirely unreliable. Aerospace engineering relies heavily upon this exact mathematical pipeline for multidisciplinary design optimization, commonly known as MDO. When mapping launch vehicles, engineers use vector algebra to establish 3D trajectories. This spatial output feeds differential equations to model shifting thrust and aerodynamic drag. Linear programming closes the loop, optimizing the fuel-mass ratio based on drag data. To optimize a single variable like fuel consumption, MDO proves you must continuously recalculate the entire mathematical chain. We can observe the same pattern by shifting the focus from aerospace to the internal hardware of a 5G electronic transceiver. Here, the spatial framework forms mesh networks of circuit traces, solved mathematically using matrices. The kinematic engine applies calculus to process analog radio frequency waveforms flowing through these pathways. Finally, conditional probability constructs digital signal processing filters, isolating true data from electromagnetic noise. While the hardware varies, both systems rely on the same logical pipeline: spatial mapping, kinematic change, and error correction. This leads directly into the third domain, computing and software architecture, which addresses how these equations are executed in practice. Software engineers rarely write raw mathematical loops from scratch. Instead, they architect unified, object-oriented numerical libraries. They translate abstract math directly into code structure. Function invertibility is repurposed to build base classes for data serialization. Monotonic intervals are translated into APIs that power search optimization algorithms. Matrix inversions are converted into accessible functions optimized specifically for 3D graphics rendering. Software architecture acts as the universal translator, converting abstract mathematical logic into automated machine execution. Your final actionable objective today is to compile your isolated local code snippets into a clean, standalone computational handbook. We will use a Python blueprint centered around a single class, the Engineering Math Toolkit. The spatial, kinematic, and error correction blocks you built over the last 6 weeks will collapse into neat, executable, object-oriented methods within this class. Structuring your code this way ensures that the complex math you have learned can be instantly imported and reused in any future project. By completing this integration step, you have successfully finished the 33-day mathematical engineering track. With this toolkit built, you are now prepared for applied thermodynamics, fluid mechanics, and advanced algorithmic design. The focus of this track is the transition from memorizing isolated equations to architecting deployable computational tools.